Start recording. So the big thing, if you're watching this recording, is so far my audio inputs do not capture the Discord voice channel traffic into the recording. So you won't be able to hear the guys that are in the Discord asking or talking or whatever until we get that straightened out. But we'll work on that for the next one. So yeah, first chapter, water supply and hose. We're gonna talk about some hydrant stuff, and we'll see how this goes. This is supposed to be a relatively long presentation, but we'll see if we can get through all of it here in a couple hours or so. Start off with
My name's Captain Dennis Laguerre. I had the privilege of writing.
This is the guy that wrote this chapter. You guys hear it okay?
In the water supply section in the Firefighter 1 and 2 handbook. I'd like you to take a moment and consider how important water supply is. Without it, you have nothing. You need water to put fires out. It's the primary extinguishing agent in the American Fire Service, even worldwide. This chapter is designed to give you the entry-level knowledge, supply hose, hydrants, accessing water from lakes, and other alternative water supplies, pools, the different types of equipment, spanners, hydrant wrenches, couplings, and hoses that you need to establish an effective water supply. So I'd like you to take a moment and think about it and then listen up, because this is extremely important. This is a bread and butter operation, and like I said, the uninterruptible water supply is critical for firefighter and life safety, and it's a main aspect of your job. My name's Captain Dennis.
Nope, just once is fine. Okay, yep, water supply and hose operations are crucial to fire extinguishment. I mean, it's kind of the main piece. There's pretty hard to argue, even if you're a truck guy. Somebody's got to do the water part here. Establishing adequate water supply is one of the first elements of a successful fire attack. That's the first thing we always do when we get on scene of a structure fire, if we've got something that's working. Failed fire attacks are often blamed on lack of water. That's definitely true. And everybody in the fire ground is responsible for water supply. So, when we get on scene, we're going to delegate who is going to be hitting the hydrant. But ultimately, everybody wants to make sure that they're at least paying attention to that somebody's doing it and that somebody's doing it properly, because everything else hinges off having water supply. Most common reason is quite obvious. It's plentiful. Water is the most abundant resource on the planet. The characteristics of water is that it absorbs a large amount of heat. There's some side effects to that heat absorption, like steam production that we'll get into in a lot of different fashions as we go along through some of these presentations here. It's definitely easily transported both through pipes and through tenders. As far as the municipal water supply and everything, it's a very established. I mean, there's pretty obvious reasons of why we use it to fight fire with, as well as we know the characteristics of what's going to happen as we put that water on the fire. The chapter goal of this lesson will introduce the students to the basic principles of water supply, applications, and fire hose principles and operations at fire incidents. These are the sections of the chapter. Basic water characteristics and terms, municipal water systems. We'll talk about some of the stuff that we have. I forgot to go to the station and get our hydrant book, but we'll look at those the next time we're down there. Rule and auxiliary water supply, introduction to hose. We'll talk about some drafting operations, some hydrant appliances, and then we'll have a summary at the end. This particular chapter is ironically one of the bigger, more in-depth chapters of the entire Firefighter 1 class. I didn't pick it that way on purpose. I think that means how it is one of the most important things. I think it was important to get everybody at least have some baseline training on water supply. So we just happened to stumble into one of the most in-depth chapters in the entire book. So we'll get through it. So chapter 1 here. Following completion, the student should be able to describe or demonstrate the following of the terms flow and pressure. Basic characteristics of water, it's wet, right? The terms static pressure, atmospheric pressure, residual pressure, friction loss, and water hammer. Non-compressible, so water, um, it's going to hold the same volume when you compress it. 1 cubic foot of water occupies 1 cubic foot regardless of pressure. So obviously you can put water under pressure, but it's still gonna occupy the same volume. Capable of being pumped, can be moved from one location to another. We've all seen that. Um, Flow is the volume of water being moved, expressed in gallons per minute, GPM. So you'll hear us say we've got a 150 GPM nozzle, or you'll say, we've got a 2000 GPM pump, or certain numbers like that. That's the main metric that we use to describe how much water we're moving. That's flow, is the amount of water that we're moving. Pressure is the force applied over a given area, expressed in pounds per square inch, or psi. So that would be us, flowing at 110 psi, or if we have a static hydrant pressure of, 60 psi or whatever we may have. That's the pressure that we have. You guys understand flow and pressure pretty well? I would bet so. Okay. Uh, Water weighs 8.33 pounds per gallon. 1 cubic foot of water holds 7.4 gallons. So 8.3 pounds per gallon. You'll hear a lot of people are just rounded to 8.5 or so, but it's just a general idea to know if you have 100 gallons of water, you're looking at, um, what's that? 833 pounds. Yep. So that gives you an idea of just how much that water weighs. So when you're hauling around a tanker weighing with 2,000 gallons of water, you're talking about a lot of weight that you're moving around there. 1 cubic foot of water holds 7.48 gallons. It sounds like pretty hard to believe. At least it does when I think about a cubic foot, right? Like 1 foot, 1 foot, 1 foot. Sure doesn't look like 7.48 gallons, but I'm no mathematician, so must be. Yeah, it doesn't sound right, does it? Not really. I think of a 5 gallon bucket, but then again, I didn't write the book. Uh, so elevation head is the pressure created by the weight of the water. So this is a huge factor if you guys end up getting into um, somewhat in standpipe operations, I guess, but we use it a lot. We think about this a lot when we're doing wildland firefighting. A lot of times, if we're pumping water downhill, just having the truck and the weight in the weight of the water within the tank, you may not even have to turn a pump off to be able to get maximum nozzle pressure at the end of that hose. If you're pumping down the side of a decently sized elevation. So 100 foot of elevation is 43 psi. 200 feet of elevation is 86 psi. So if you're pumping downhill, and again we're in pretty flat prairie out here, obviously, but if you're moving water downhill, you may be bypassing because you have so much pressure. Um, but it makes a big difference, the amount of gravity and its effect on the weight of that water. So rough estimate of 5 psi needed to move water up 10 feet. So it's relatively the same going both directions, right? So if you need to move water up 10 feet, you will lose 5 psi. So that will come into play when it comes to standpipe operations. If we're pumping up like out there at Pawnee even, or even some of our 3-story apartment buildings that we have here, if we're pumping up 30 feet, that's an extra 15 psi. If we're pumping up 40 feet, that's an extra 20 psi that needs to be accounted for when you're pumping those standpipes. Pumpers provide pressure to move water through hoses and 2 upper stories of a building. Yep, for sure. It's the best way. Um, so atmospheric pressure is what we're talking about here. Force of the weight of the Earth's atmosphere. So this is just standard pressure all around us, right? Which is 14.7 psi at sea level. I'd be curious to see, what we are right now. Probably depends on the day, but um, being that we're at 4,000 or feet or whatever, we're probably a little bit less than 14.7 psi. Um, Any idea, Tristan, what our PSI is at atmospheric pressure here? Nah, probably not. Yeah. When a vacuum is created, atmospheric pressure pushes a liquid up a vessel. When a vacuum is created, atmospheric pressure pushes a liquid up a vessel. So if you're if you're creating a vacuum, you're lowering that pressure below atmospheric pressure, which is going to then draw liquid, just like oh yeah, with the straw here. So you're drawing the liquid up there, in a sense by creating a vacuum of sorts. So something to think about when it comes to drafting is their example here. You're basically creating a vacuum on one end. You're lowering the pressure. You're sucking the atmospheric pressure out of that tube. You're sucking that 14.7 psi eventually down to 0, and then down into the negative pressure. And that's what's going to suck the water up out of that body of water down here, or a drop tank or whatever you're doing. So that's the general idea behind sucking the water up when you're doing drafting operations. And then pressure is the opposite of vacuum. That's generated by gravity, by pumping, or both. So both of those are going to have an effect on pressure. Pressure is our number one metric when we're discussing pump operations and when we're discussing anything really having to do with flowing water. Um, and I only say pressure is the number one metric because pressure is what directly affects the flow, which is again the GPM. Welcome, Garrett. Hey, good to see you, buddy. Can you see everything okay, or you need help getting it set up? We'll give Garrett a minute here because we want to make sure that he can get in here all right. Let me go ahead and call him. Getting her? Can you hear us, Garrett? He's got his mic muted. I wonder if he can. There we go. Nice, nice. Okay, did you figure out how to start the stream? Nice. So you can see my screen and me. I'm glad to hear it. Nice work. Nice work. Okay. So yeah, Derek, just to catch you up to this point, we were basically going over some characteristics of when we talk about water moving. We talk about using it in flow and pressure. How do we how do we measure flow, Zach? What do we measure flow with? Gallons per minute. Close enough. Yeah, GPM. We measure how much water we're moving by GPM, gallons per minute, and we measure pressure by PSI. And those are kind of the things that drive what we're looking for how much water we're getting on that fire. Friction loss. So pressure is lost due to water rubbing against the inside of the hose. Loss decreases if the hose diameter is increased, and higher flows generate higher friction loss in the same size hose. So if you think of flowing water through that hose, that as that water rubs against the inside of the hose, or that hose itself is slowing down how much and how easily, which is our pressure, is how much force that water has being pushed through that hose. So, and then it says that pressure loss or friction loss decreases as the size of the hose is increased. So we have more friction loss, we have more pressure lost with an 1 3/4 hose than we do with a 2.5 inch hose, which seems obvious, right? You have a bigger hose, so you're able to move more water, but you also have less circumference of hose versus the volume of the water that you're moving. So, the bigger the hose, the more volume of water that you have, and the less of that volume, the less percentage of that volume that is touching the edges of the hose. Does that make sense, man? I almost wonder if I overcomplicated that a little bit, but you guys understand how friction loss can be affected by the hose diameter? Yeah, very cool. Yep. Yeah. And so one thing that you'll see, like our tower, for example, we use two twin 3 inch um, large diameter hose lays from a hydrant supply hoses. We'll use two 3 inch supply hoses in replacement of one 5 inch supply hose. But that 5 inch, that single 5 inch is still going to be superior when it comes to friction loss. But yeah, pretty basic stuff here. So pressure types. So Dory, actually, Senior Mike Dory had a pretty good explanation that I had heard the other night about the way he describes the difference in pressure types. Mike says that static pressure is pressure whenever you have to pee, you have to take a piss real bad. The pressure that you feel is static pressure, and then the residual pressure is how hard that thing's peeing whenever you're going. So you can I have to thank Mike when you see him for that analogy, but that's the basic concept. When you're not flowing water, the amount of pressure that you have, that's the static pressure. That's how much pressure you have um, not flowing water. So it's completely irrelevant to how much water is behind there. You can get a pressure washer hose if you've got a pressure washer, or if you have a pressure washer at work, if you've ever even seen a pressure washer, I'm sure. You can have the same. You can have 100 psi. Get 300 psi of pressure washer pressure. Um, but as soon as you open that pressure up into flowing through a hose, now the amount of water that you're actually flowing through there is going to affect the residual pressure that you have while you're flowing water. So why is this important? So when we first pull a hose line and we charge it up, um, we can't set the static pressure is not important to us. The static pressure doesn't mean anything to the person on the nozzle or the person at the engine when it comes to charging that hand line. We need to know what the pressure is when it's flowing water. Um, so that's why we have to be setting the pressure at the pump with the water flowing, if that makes sense. So we have to have the water flowing through the nozzle to get the correct pressure set at the pump. Uh, Water hammer. Um, so this is the violent dissipation of kinetic energy when water is stopped quickly. It's created by closing intakes, discharges, and nozzles too fast. Nozzles and valves should be operated slowly. So a lot of times, you can see this if you slam a gate valve, like so, say you're filling up one of the trucks off the hydrant, and the water overflows off the top, and you run over there and you slam that valve shut on the side of the truck, you can see that whatever that 2.5 hose that you're filling with, you can see it jump on the ground. You can see it shake, or you can see it, even jump up off the ground a couple of inches if you got a lot of pressure there. What you're doing is you're basically hammering the system. In our old station, we had all of our overhead fills and stuff for the trucks. Um, and so like we wouldn't have the hose on the ground like we do now. We would fill them all from an overhead dump basically. There was pressurized pipes running in the top of the station. You'd climb up onto the truck and you'd take that flexible hose and you just stick it into the top of the tank and you would fill it up that way. Well, if you would shut that valve too fast, all the plumbing in the ceiling of the fire station would all shake in its mounts, and you were really worried you were going to break something. But so That's the idea of a water hammer. That's why anytime we're closing a valve, we always want to do it smooth and controlled. Even on the nozzle, like this guy is closing his nozzle here, when you're shutting down a nozzle, you just want to be just smooth, not like slamming it back and forth, because you could one water hammer the truck or water hammer some of your appliances, but you could also be able to increase the pressure to another hose line quicker than the truck can react. Um, we'll talk about that at another date too. But the general idea is you want to close some of that stuff pretty slowly. Okay, any questions on the measurement and the terminology when it comes to measuring water movement? Yeah, nerd shit. I like it. I like it. So we'll get into municipal water systems, and I am unfortunately I am not an expert when it comes to our hometown municipal water system. I don't know enough about it, and there's a lot to know about it. We've had people on our department that were actually on the water department, and they would know everything about it. So unfortunately, those guys are not here tonight, so uh, we'll make do. But we do have those hydrant books. Has anybody not seen those hydrant books in our engines? I should have brought one. I had planned to bring one with me, but I couldn't make it to town today. But they're basically a book that gives the layout of all the hydrants in our community, and then it will tell the size of the main and whether it's a 4-inch main or a 5-inch main that supplies those hydrants, so you can get a good idea uh, of which hydrants are better than others, because some certainly are. So following completion of the municipal water system section, the student should be able to describe or demonstrate the following: the critical elements of a municipal water supply system, common sources of water, 2 common types of fire hydrants, procedures for opening and closing a hydrant, and what is included in an annual hydrant test. All right, so what we usually have, so these municipal water systems are usually run by public or private water departments. Ours is run by the city. Supplies water for consumption, obviously, so drinking water, everything inside the house. Also supplies water for fire suppression. All the hydrants that we have are used for both. We don't have any gray water hydrants in our area, at least that I know of. Groundwater stored underground in aquifers and wells are drilled and the water is pumped out. Surface water, lakes, rivers, reservoirs. Many systems are beginning to rely on both ground and surface water. Um, so ours is out there by like the Brush Pond, like just south on 28. Let me see if I can just pull up a map here. No, it'd be out here. They have a lot of wells that are supplying the majority of our city water. And then they pump it up here to the water towers. And then out of the water towers, these are the water towers. You guys are familiar with them. Out of here, it all drains up over down this direction. And here's where we have our wastewater treatment facility, to where they try to reclaim as much of it as they can. It's accurate as far as I know. I'm sure there's more to it than that. Like I said, I'm not an expert on it, but I do know that much. Okay. Um, yep. So most of ours is from groundwater. Water is treated by chemical or mechanical means. So it's either, just like it sounds, either treated with chemicals or it's going to be filtered out with different filters. I'm not sure how they do it. I assume they do it at a system of both at our water treatment facility. Treated in order to make it fit for human consumption. That way it's potable. Um, the most important part of the municipal water system is the distribution system, designed to maintain safe water quality. Meets fire flow requirements for the municipality. Here they have a diagram that's talking about some interesting stuff. I think a lot of this is being um, related to elevation changes, because that is one of the main thing in a lot of communities is elevation obviously has a huge effect on the amount of pressure that you get at your hydrants. We do have boost pumps, I believe, that take care of if we have a pressure demand increase from fighting fire. There's boost pumps at the water towers that'll kick on to help maintain, because our water towers are obviously not this tall. So a lot of towns will use gravity to supply water to the main grid. Since we don't have a lot of elevation deals, we don't need quite so much gravity. Uh, Tanks are pumped full at night during low usage times. Makes sense to me. Designed to have low friction loss and good residual pressure. Uh-huh. Large diameter pipes supply medium and small pipes. Just like most plumbing situations, you're going to start with larger pipes and you're going to step down as needed. And the main reason for that is because, like we talked about, friction loss. The larger diameter pipe that you have, the less friction loss that you have. So generally, you're going to use as large diameter as you can justify the cost. Grid layouts allow water to be received from multiple directions. Water main valves located at frequent intervals, commonly 500 to 800 feet apart, often left in the open position. Small areas can be isolated for repairs. So these can turn off, a few houses, or maybe in individual apartment complex, or something like that. We have to get the. Usually we let the city take care of turning those off for us. We don't do that. We call the water department to come turn those off and on. Primary feeders are often 30 to 48 inches in diameter. Typically, no hydrants are connected to these primary feeders. May be larger for cities with high demand. I don't have enough knowledge with our community to know anything about our primary feeders. I apologize for that, guys. Secondary feeders are generally 12 to 24 inches in diameter. Many hydrants are connected to these secondary feeders. Again, I cannot give any insight on this. The distributors, um, this I do know a little bit about with ours. They range from 4 to 12 inches. Most of ours are 4 inch at the minimum, commonly 5, and then I think we do have some 6s as well. I don't know that we have much that's larger than that. There might be a few, but I think the most common that we have are 5 and 6 inch. A majority of water mains are this size. Hydrants are primarily installed on these small distributors. So that's one of the main things that we use the hydrant book that we have in both of our engines for, is to look at the layout of the hydrants and determine what size these distributor plumbing is made of. That way we can get a good idea of how much flow we're going to get out of the hydrants that are connected to them. So hydrants, we've all seen one. I have one in my yard. It's fake. Main access points for fire department water supply, right? Connected to the water main, usually by a 6 inch pipe. So a 6 inch pipe is going to go from the bottom of this hydrant down to the water main. Then the depth of that will depend on the community. I'm not sure how deep ours are, but I don't think they're crazy deep. Often fed from two directions. So a lot of times they're installed in a loop. Um, I don't know if we have any dead end hydrants. I assume we do. Um, but I'd have to look at the hydrant book to be sure. But dead end hydrants are fed only from one direction, less capacity than other hydrants, may be marked to indicate dead end. Ours As far as I know, we do not have any kind of marking system on our hydrants. Hydrant types. Wet barrel hydrants. Water fills the hydrant at street level, used in warm climates. So you will not find any wet barrel hydrants in Colorado, at least that I know of. With it just gets too cold here. Maybe Florida though. Maybe Texas. Maybe Arizona. I'm not sure. But they're basically charged all the time. I mean, you can see there's no valve down here. They're gonna have water here at all times. Fills the hydrant at street level. Dry barrel hydrants, which is what we have in our community. Water stays below the frost line until opened, used in freezing climates. So as you open the top of it right here, it turns this stem that goes all the way down to the bottom, and it pulls this valve up right here. And that's what allows the water to flow past this valve and charge the hydrant itself. Once you close the hydrant, you turn this all the way back down, and the water that's all still up here drains back down the hydrant and out this drain hole or this weep hole right here. And that way it drains the water back out, and it lets the hydrant not retain water in it so it doesn't freeze, because we don't want to break them. They're very expensive and labor intensive to replace. Hydrant connections typically use national standard hose thread. All of ours do. Some cities have different thread. Um, yeah, I don't know much about how common it is to have a different thread. Some hydrants incorporate a Storz connection. Our hydrants do not incorporate a Storz connection. We use Storz adapters, and we'll talk about Storz and Storz adapters here in a little bit. Number of outlets varies. One or two 2.5-inch outlets. That's the ones on the side here. These are two 2.5-inch outlets and one steamer. The steamer is what we call the large outlet. Um, in our community, we have a pretty decent mixture of both. We have a pretty most of the departments that we have will look just like this. They'll have a 2.5 on each side, just like the one behind our station, and they'll have a steamer connection in the center. But you will find quite a few hydrants that we have that do not have the steamer connection at all. They only have the 2.5 connections on a lot of the hydrants in our community. So if you've looked in our hydrant bag, and again, we'll get to that when we get down to the station and start putting some of this stuff into action, you will notice that we have a Siamese gate valve. Let me see if I can find something here. Not a gate valve, a Siamese Y firefighting. Yep, bad boy right there. 600 bucks. Golly. So you'll have one of these in each of the hydrant bags on our engines, and we have these pony sections, right? These little 20-foot sections of 2.5-inch or 3-inch hose actually that will connect here and here, and we'll connect that to either side of this, and then we'll connect our 5-inch LDH to this end, and it will basically just an adapter basically. So the most important thing to recognize with this is that as soon as you get off the truck at our structure fire, even though we're all thinking about fighting that fire, we just want to make sure that we're looking at the hydrant as we get off and taking the correct. If we need to bring the pony sections of hose with us, nothing's worse than having to go 3 blocks down or get on the radio and try to get the truck to stop because they drove off with the pony sections that you needed. And then you turn around and realize that, like, oh shit, now we're in a real bad spot because now we've got a hydrant that we can't connect to. So we'll definitely hit that point a few times over the next few weeks here. So your basic flow chart of operations, like we said, size up the hydrant. As soon as you get off the truck and if you're the hydrant guy, or if you and maybe even you and another guy are going to be the hydrant guy because it's that important, you're going to get off the truck, you're going to look at that hydrant, you're going to size it up. Is it accessible? Does it look operable? Does it look like it's been, ran over or hit or something like that? Does it have a steamer connection on it? That's the main thing that we want to be thinking about. Does it have a steamer? Or do I need to bring the pony sections and that Siamese Y that we just looked at? Okay, then you're going to get the tools that you need. You're going to grab that 5-inch section. You're going to take all of your tools as you're carrying it all over to that hydrant. You're going to set it all down. You're going to wrap that hose around the hydrant. The truck's going to drive off. It's going to lay all the hose on the ground. And as soon as you can recognize that the hose is not going to, snag in the truck, then you can get to work on the hydrant. Once you get to work on the hydrant, the very first thing we're going to do is we're going to flush that hydrant. So we're going to pop off that steamer connection, or pop off the cap on the steamer, right? Um, Pop that bad boy off. We're going to open this thing up all the way. Open the hydrant up all the way. It's going to start squirting out of here, and it's going to usually come out rust colored. It's going to blow any sediment. That hydrant may not have been used in a year. They should be testing the hydrants every year. How often that actually happens these days, I don't know. I would assume that they're probably pretty good at it. But even after sitting for just a year, it'll get a lot of sediment built up at that section of the hydrant, and you don't want to pump that stuff through your nice fire trucks. We flush it out onto the ground. As soon as it runs clear, you start turning that valve all back down, turn the hydrant back off. Once it's shut down, then you're going to connect either directly your Storts adapter and then your LDH, or you're going to connect your Siamese Y and get that thing ready that way. Um, and then it's a good idea. Usually, we'll try to put it in the habit of just putting on that gate valve on the side of the hydrant. It's just there's situations where you might just need a 2.5-inch connection on the side, whether it's for a backup or whether for something else. So it's just good practice to put that gate valve on there. And from there, you're ready to slowly open the hydrant whenever the engineer is ready for it. And after we open the hydrant slowly, we just want to make sure we open it up all the way. Okay. And again, it'll be a lot more sensible and it'll be a lot more enjoyable when we're actually hooking up to one of these hydrants a couple weeks from now. And what we'll probably do is we'll probably hit a few different ones through the town so we can get a good idea of sizing it up and what the different ones might look like. So hydrant spacing, typically 300 to 500 feet. Again, if I wish I had my book, but every few blocks or so, you're going to find a hydrant. And they should be inspected annually. Like I said, I think our water department is pretty good at that. But then again, everybody's busy these days. I don't know. So your hydrant inspection, your size up. Well, I guess this isn't a size up, but it's just a hydrant inspection. This looks like probably their annual inspection. Location, clearance. Did somebody put a bunch of yard decorations or yard trash, around this hydrant? Um, Caps, are they movable? Are they seized up? Are they still there? Are they cracked? Are the chains still there so that we don't lose the caps when we take them off? Are the threads good to where the caps aren't going to blow off once we charge this hydrant? Is there trash in the barrel? This is the barrel right here. Do the valves work properly? Does it painted to look nice? Is it broke like this one here? Color code, again, like I said, I don't think we use any kind of color coding on the hydrants, but if anybody watching this video uh, will correct me, possibly. I know that all the hydrants that I know of uh, in our town are either red or red and white, but reflectors, some of them may have reflectors on them. Hydrant gate and curb paint. The curb should be painted to designate not to park here. Some areas do use hydrant color coding. They use it to describe the GPM, which again is the flow that hydrant is capable of providing. Um, as far as I know, we don't have anything like this here. So this may be a test thing, so we better go through it. Red they use for less than 500 GPM, orange 500 to 1000 GPM, green 1000 to 1500, and light blue 15 GPM, 1500 GPM and above. So We'll see how imperative that becomes later. Hydrant flow testing. This is something that I believe that they do in our community whenever they test the hydrants. Coordinate with the water department, provides maximum flow for the hydrant, and indicates problems with the water supply in the area. So they'll use a flow gauge and they'll see just how much GPM or flow that they're getting out of that hydrant. Okay, any questions on fire hydrants? So typically, if you pull up on scene and there's a vehicle blocking your hydrant, you know, a lot of times it is possible to still, route the hose over the hood or, underneath the vehicle or in front of the vehicle. Um, you can look at it and see if the hydrant's set back far enough where you could still make it work. Um, if it ends up being one of those deals where you break somebody's windows out and you run the hose through it, it is what it is. But uh, ultimately you're just going to have to assess the situation individually and find the best course of action. And I think that it's important to not lose sight of the main issue at the time. So whenever you're trying to hit a fire hydrant, the main issue is that the bottom line is no matter how frustrating it may be that this person parked in front of this fire hydrant, the bottom line is that we need to get water on the fire as quickly as possible. And so if there's another hydrant that you know, may be an option, maybe that's just the best option, and we can fight that fire after the incident is, or fight that fight after the incident is complete. But we'll have to look at every situation individually and figure out what the best plan of attack would be. But yeah, nothing's out of the question. Yep. Anything else? Cool. Hydrants are fun. We'll spend a lot of time hitting hydrants. Okay, rule and auxiliary are water supply. This can be quite a bit more complex. Following completion of this section, we should all be able to describe and demonstrate the following: common types of auxiliary water supplies used by the fire service, a basic water shuttle operation, common static water sources used by the fire service, procedures for a basic relay, the purpose of a fire boat, and dry main system. Boy, I don't know much about that. Rural water. So this is something that's very important to us, right? For obvious reasons. Many firefighters work in areas that are not served by hydrants. The majority of our district is not served by hydrants, at least by square miles. Population-wise, there's probably more that have hydrants that don't, but there's still a significant amount that do not have any hydrant system. Adequate water must still be supplied for effective fire attack. But just to give an idea, and then reliable sources of water must be identified and planned. So just to give an idea, um, we've got decent hydrant operations, obviously all through town right here. Um, Going as far out as about in here would probably be getting pretty close to the last hydrant. Um, and then out south, we've got them as far as Cogen out here. I think that there should be one like right there maybe. I think right there is a hydrant. But there's not a lot of pressure out here. It's not a very big main. A lot of times, when we're running a water shuttle from out south here, it's usually quicker to drive and fill up at the water tower down here. We usually try to do this one. That way we can just leave our leave our equipment out there. We've got a big area to pull in, turn around. Usually the gate's open. So that's usually the best option for fill. There's plenty of pressure right here, and it's faster to drive the extra quarter mile up in here and fill off this one than it is to fill off this hydrant down here because there's not a lot of pressure on that guy. Um, and then out north here, there's hydrants all along here. There's hydrants all along here. There's hydrants. Um, Obviously, they're not serving much, but there is water out there. Um, and then as far as east goes, I think it pretty well stops at that, like this area right here. I assume you guys have hydrants over there. Yeah, there's one right there. Yep, right there. Yep. So yeah, they're out there, but they, you know, something to keep in mind is just having a good idea of where you're going, and hopefully there's enough people to where you don't have to wait to get on scene. Oh shit, there's not a hydrant here, guys. We gotta get tenders out here. So um, we'll spend some time, um, you know, really studying where our hydrant services end because we want to know right away if we got to get tenders coming or if we've got a large structure fire, if we've got to get mutual aid tenders coming, because you don't want to run out of water during your initial push there. So something to think about. So adequate water must still be supplied for effective fire attack. Yeah, we can't necessarily. I mean, we can, but we don't necessarily want to change our firefighting tactics based on whether we're on rural water supply. I mean, obviously we will, right? Like we're not going to set the tower up and just go hog crazy if we're fighting fire off drop tanks, but um, but we don't want to get to the point where we're, only flowing one hose line because we, screwed up our tender operation or couldn't get enough people down there to get all the tenders out. So lots to think about though. Reliable sources of water must be identified and planned. So whether we're going to drive back to the station, or not to the station, but to, where our fill up spot's going to be, depending on where we're fighting fire at. Are we going to fill up like we talked about at the water tower there, or are we going to drive over to, one of the hydrants on, somewhere else to fill up, or what are we going to use? We just want to have an idea. So water tenders is the primary way that we are going to get water to rural firefighting operations. Modern fire engines carry 1,000 gallons of water or less. Yeah, 921 and 920. I mean, they're like 500 or 600 gallons. They're either way, they're not much water. And we've seen in the few pumping operations that we've done, like when you start flowing water, like you've got very few seconds before you got to start thinking about what plan B is because you do not have much, especially when you're flowing a big hose. Now, if you know that you're pulled up on a rural structure fire and you know that that second truck is, just leaving the station and you're a 5-minute drive and you're already on scene, um, you may have to rethink about what your attack's going to be. You're probably only going to pull 1 1/3 inch hand line, and you're just going to have to be as effective as you can with the 500 gallons of water that you have on scene. And not overcommit yourselves and your bodies to where if you can't knock the fire down with that 500 gallons that you do have, that you still have a good clear egress back out of the house or shop or whatever. Water tenders have drop tanks, or sorry, have internal tanks that can hold up to 45 gallons of water, 4,500 gallons of water. I believe our tenders, I think one is 2,000 or 2,500, and I think one is 3,000 or 3,500. I'd have to check and see, but I know that they're a shitload of water. I mean, they're a lot of water for compared to how tenders used to be. Back when I first got on, they've come a long way with hauling water to scenes. So a water shuttle. What? What's up? No. Water shuttles can provide large fire flows. I'm sorry, efficient water shuttles. So water shuttles is usually kind of the most important part, right? So we're gonna bring tenders in, we're gonna dump them into drop tanks. They're gonna turn around and they're gonna fill, and then they're gonna return and they're gonna dump into a drop tank. And we're just gonna shuttle water. We're gonna do that loop, fill and dump, and that might be a 20-minute turnaround. So it usually takes um, at least two tenders to have an effective water shuttle, depending on how far you are from town. Um, so the dump site located at the fire, right next to the engine, just like we have here. Portable tanks filled by tenders, which are our drop tanks. You guys have seen these. If not, you will. Attack engines, which is our 921 or 920, draft from these tanks. And then water tenders travel from the dump site to the fill site. So they'll dump here, they'll return to the water tower or wherever they're going to, and they'll refill, and then they'll return back here and just keep these things topped off as well as they can. The fill site, located as close as possible to the fire, should have a capacity of 1,000 GPM or more. So you want a good hydrant that's going to fill a truck fast. Um, and you want it to be as close of a turnaround as you can. Static sources or hydrants may be used. Um, so there are some wells out south with overhead fills. Some farmers have set up some overhead fills way out south. I'd have to try to get some reminder about where they are. But the general issue with them is there's not enough water flow to justify the amount of time that it takes to wait to fill the tender. It's usually quicker to drive back to town, fill off the hydrant than it is to fill off one of those well pumps out there. So we don't use them. We've had people put them in, and we've used them a couple times, but it's faster to drive to town. Basic water shuttle follows a cycle throughout the incident. So, like we said, dump at the fill site. Uh, wait. Dump site at the fire. Route to the fill site. Tender filled at the fill site. Return to the fire. So, like we talked about, you're just dump and return. Water shuttle safety. This is definitely can be a very dangerous operation. Never increase water delivery by speeding up. You're not going to make that big of a difference by driving that fast to where it's dangerous. Training will increase safety and efficiency. Increases in delivery are made by adding more tenders to the cycle. So if you're not getting enough water fast enough, we need more trucks. You can never drive fast enough to make up the difference for adding an extra truck. Um, but we've talked about how driving is dangerous multiple times, and we will continue to do so. Typical static water sources, lakes, rivers, and ponds. So we do have one static water source. We'd really only use it in case of an emergency, but it is important to know. I think it's in here. I've never seen it, but I'm pretty sure it might be in there. There's a spot where you can actually draft out of that pond. Um, we might have to go on a scavenger hunt to see if we can find it one of these days. But I'm pretty sure that that's where it was at, unless it's clear down here. Maybe it's this. That might be it right there. But there's a spot. It's one of those two spots. I don't know what that is. It might be that. Looks goofy to me though. I bet it's where I originally thought. Either way, there is a spot where we can actually draft out of this pond, which if we ever have a major problem, it would be good to know about. Be hard to press to find a situation where we'd use that, but you never know. With that being said, that pond is not really in a location to where we could back up and draft out of it very easily. The banks just aren't quite designed for it. But some places do have streams. We could draft out of some ditches. Um, but again, if we're close enough to draft out of a ditch, we're close enough to uh, just go to town. What about one more static water source that you guys can think of that's not mentioned here? Maybe quite a bit smaller. Swimming pools, yep, swimming pools. That's usually a couple thousand gallons. Swimming pools and sock tanks is kind of the big one that we have out here. You could easily pull 1,000 gallons out of a stock tank if you were fighting a grass fire out there. And we do, if it's not too nasty. Drafting hydrants. Hey, yeah, that's what we were talking about. Somewhere there is a drafting hydrant for our pond. Can provide full is a specialty hydrant. Can provide full pump capacity, ideally less than 10 feet of lift. Um, so you don't want it too high above uh, where your water table is at. Submerged strainers so that you don't suck up a bunch of fish or dead detritus or branches or whatever. Female swivel for drafting hose attachment. So again, we'll have to see if we can find that thing because I know it's there. I've heard about it. Hard suction. Have you guys seen the hard suction? Most of our trucks have hard suction on them. Attaches the pumper to the drafting hydrant or to, our water source or whatever. Drafting operations can also be conducted by placing the hard suction directly in the water with a strainer on the end. Again, the strainer is super important because you don't want to suck up like leaves and sticks and stuff. You don't want that stuff going through your pump. Um, but the hard suction, you guys have all seen the hard suction, right? Maybe this stuff right here. And then these are also these we have little hard suctions on the back of 925 and coiled up in the compartments on 924 and on top of 926. There's the littler ones, and then there's the bigger ones on the tenders and on the main engines. But yeah, the hard suction is the hard hose that we use for drafting. That way, when you pull vacuum on it, it doesn't collapse. You can't, you know, draft through a hose that will collapse whenever you pull vacuum on it, obviously. Cisterns. So we don't really have cisterns in our area. They're underground water storage tanks. There are cisterns at some of the places out south, not like way out south, like southwest Washington County, um, like clear out like Last Chance area, where they're having some problems running out of groundwater. There's people that are having to haul water into cisterns, but can be used for drafting during fire emergencies. Even on my wildland deployments, I've never drafted out of a cistern, but I guess you probably could. Jet siphons. Okay, so we've used jet siphons on one, maybe two calls that I've been on. They're very cool. We've used them on uh, on a big haystack fire that we had. It was actually we had a haystack fire out south, and we had like four drop tanks set up, and then we would siphon, um, to kind of get because the truck was drafting out of one, and then we would dump the tenders. We had so many tenders that they would fill up the other three, and then we would just keep trying to balance them out so that whenever a tender would show up, you wouldn't have four tanks because okay, so if you just do like a regular siphon, right, where like if you would siphon like these two tanks together, they're going to equalize and they're going to go down at the same level. So like you could theoretically tie all four tanks together and they're all going to drop down at the same level, which sounds good, right? You're accomplishing the same thing. The problem is whenever you have a tender that shows up to dump, if all four tanks can only take 500 gallons, it makes it a giant pain in the ass for that tender to dump. So if you set up a jet siphon system, then you can jet siphon the water out of this tank into this tank, and then you could equalize these, or you could jet siphon both of these tanks into these two tanks and you could equalize them. That way, whenever a tender shows up, there is an empty tank for it to dump into, if that makes sense. Um, and I think we'll probably get into how a jet siphon works here, but it talks about typically used to transfer water between portable tanks, like we talked about. A siphon is attached to the hard suction. Water supplied to the device from, water supplied to the device siphons from one tank to another. So, wow, there's nothing in there about jet siphoning. Good night. Okay. Well, the basic concept is that if you have water and you have a hose that has a like a regular old siphon, that hose is full of water. But if you push water through a nozzle, have you guys ever heard of like a Venturi effect? It's the same kind of concept. As you force even a small amount of water, like an inch and three-quarter hose, you force that through that large suction, it's going to draw in other water around it through that Venturi effect, and it's going to force more water to go in there, and really jet siphon. We might have to set one up one day to explain it. It's kind of hard to explain with your hands and airplanes and stuff, but does that make sense to anybody? Maybe. Yeah, yeah, I like that. It's a good explanation. So for those that couldn't hear, Dory was explaining, Tristan was explaining that water is attracted to itself. So um, just like a sheep in a herd, if one sheep goes, the rest of the herd is going to follow. Whenever a few or a handful of water molecules go, the rest of the water molecules in the general vicinity are going to naturally want to go with it, and so it's gonna force it through that hose. Huh. Yeah, I mean, maybe I'd have to kind of set up something like that and see. Let's try this. Let's try this and see what I've never watched this, so this could be stupid, but it's only 2 minutes. Like we're not out much. Okay, so this is their hard suction. They're filling up this tank right here. This you couldn't see. Okay, so you can see that I can't really zoom in here. I don't think I can. Oh yeah, I can. No, I cannot. Oh yes, I can. Get some. All right, so uh, this is their foot or their low level strainer. So that's the strainer that goes on the end of their hard suction. This is an 1 3/4 hose that attaches to this. So this shows they're going to charge this, and it's going to shoot water through that hose. They're going to pressurize this. This hose is going to shoot water up through here, and it's going to draw in all the other water around it. It's an interesting way to zoom. Nice mask, guy. So right now, it's obviously not flowing any water. It's going to take them forever to fill this thing. Oh no, they skip it. No, they don't. 45 millimeter, uh-huh. So they put their 1 3/4 line to the jet siphon. Um, Now they're going to charge it here. The other thing that this does is it helps to start that draft a little bit easier. There they charged it. There you go. Now it's flowing in there. So part of what's coming out is the water that's flowing through that hose, but a lot of what's coming out is what is also being drawn in around that. So this will slowly drop that water level. Yeah, that was an okay demonstration at best, but thanks for the effort, guys. All right, so we'll come back to that. We'll set it up. That'll be sweet. Relay pumping. So one pump supplies water to another pump through a hose, typically used to overcome long distance from the fire to the water source. Friction loss is the main reason for establishing a relay pumping operation. So they're drafting from a pond. Well, drafting alone takes a lot of pump capacity. Then they're going to pump it uphill and distance to the relay pumper, and then they got to pump it farther to get it to the pumper, the attack pumper, who then needs more pressure to be able to fight the fire. So they're boosting their pump capacity as that goes along. Relay pumping considerations factors in the size of the hose, the length of the lay, the GPM required, the elevation change, and the number of pumpers that you have available. Relay pumping training is an important part of relay pumping operations. Yeah, you're going to want to have done this before you try to do it on scene. Specialized apparatus, specialized equipment, and pump pressures. I don't know about that. When we've done relay pumping, we've used the trucks that we already have, and I don't know that we have any specialized equipment for our relay pumping operations. But when we have used it, the primary reason was to supply water to our tower. The tower was quite a long ways away from the hydrant, and we don't carry 5-inch on our tower like we talked about. We carry 2 3-inch. And so we used 921, that white truck behind the fire station, as our relay pumper to pump to the tower, and then the tower would pump, up to the platform, and then I pumped the platform and I pumped the hose lines as well. And then we had 921 supplying me as a relay pumper. Um, but basically the concept is to just boost the amount of pressure and capacity that you have available. Uh, Fireboats and dry main systems. Fireboats can be used to supply water for firefighting. Well, we're not going to have that around here. Auxiliary water mains are separate from domestic water and supply water for firefighting. Yep, fireboats would be cool though. This is talking about reclaimed water, also known as gray water. So, technically there's probably some gray water out there at the water treatment facility, whether it's, coming from storm runoff or people's homes, it's all going to go down to that facility and would be considered gray water until it's treated. Used where potable water is not needed. Hydrants are being installed on these water mains. I don't know of anything like that in our community, but it's good to know about. This is interesting. I've never seen caps like that. Some kind of special wrench, I guess. Water supply summary. So adequate water supply is very successful, or sorry, very important to a successful fire attack. Yeah. Needed to last the entire incident without interruption. Poor water supply equals poor service. So I mean that really is the deciding factor when it comes to uh, any firefighting operation is how much water you need versus how much water you can supply. Okay. Any questions on rural water supply or fireboats? If anybody wants to talk about fireboats. Okay. Yep. Yep. We do a lot of rural water supply operations, obviously, and um, drop tanks. The biggest thing about drop tanks is that they're a pain in the ass to set up and tear down. Um, but we will use them multiple times throughout our careers, so we'll get good at the concepts. I will say that nothing is worse. There's nothing that's ever worse than needing water on the scene of a fire, whether it's a grass fire or a structure fire or any other kind of fire, and either have a truck or an engineer that is incapable of pulling a draft. So please, in your careers, whether it's with us or any other department, learn how to draft water from a standing static source because um, it can be tricky to get right. It can be tricky to get efficient at it, and every truck is going to have its own little quirks that you've just got to know how to work around. Um, and a lot of it is just being able to kind of get a feel for what's going on and hear the changes and what's happening. But I mean, nothing is more important than being able to pull a draft because getting on scene and trying to fight a structure fire and nobody can get a draft acquired on the engine. It has happened before and it is an absolute embarrassing nightmare. So don't let it happen to you. Okay, water supply and hose. Introduction to hose. Hoses. Following completion, we should all know the general classifications of fire hose, parts of fire hose construction, type and size of fire hose used and the flows associated with them, the difference between threaded couplings and Storz couplings. 3 ways of coupling fire hose, common problems to look for when inspecting firehouse couplings. Interesting. I would not have expected a typo in here. 5 different types of hose fittings and 4 types of hose appliances. Oh my gosh. And 4 types of hose tools, proper procedure for conducting an annual hose test, 2 types of pre-connected hose loads, 3 types of hose rolls, difference between a forward lay, reverse lay, and split lay, difference between a flat load, horseshoe load, and accordion load. I don't know if that's right either. Hose is specially designed for the fire service. The hose that we use is anyway. Characteristics, low friction loss, durability, lightweight, and ease of coupling. Those are all very important to us. Classification hose, based on tactical uses. So we have wildland hose, we have booster hose, we have drafting hose, we have supply hose, and we have attack hose. So these are all things that we use within our station. Wildland hose is single jacket. I'm sure we'll get into them. Yep. Drafting hoses. What's what we talked about? We called it hard suction. That's what we call it here. Rigid hose used for drafting from a static water source. That's what we stick into the drop tank. Hard ribbed. It's also like a smoky clear color so that you can see through it, so that you can see the air being replaced with water. You can see how close you are to getting a good draft. If you have any air bubbles coming through. It is not designed to be used with a pressurized water source. It is only designed to be used under a vacuum. Supply hose, which is our LDH, pretty hard to miss at our station or at any. It's made of rubber or some rubberized material, designed to move large volumes of water. Larger diameter than attack hoses. Not all of our, most of our LDH is 5 inch, with the exception of what's on the tower, which is 3 inch. And with the exception of some of our small pony sections that we use for filling hose, like on the back of the tenders. Even though it is yellow and rubberized, it is not 5 inch, that is 4 inch hose. Attack hose, large. The attack hoses are what we're all familiar with. That's our inch and an inch and 3/4. That's our 2.5. They are large enough to move the required flow. They're lightweight enough to be moved around by firefighters, both internally in homes and externally. Wildland hose works well on wildland fires. We have wildland hose on, if you've seen those black backpack looking things in 924 or 926 or on the back of 925, those are filled with wildland hose. The benefits of this is that they're single jacket. They're not double jacket like our structure hose is. They're single jacket, so they're much lighter, um, and frankly cheaper. Diameters no greater than 1.5 inches. Most of what we use in brush is inch, um, with 1.5 inch supply. So we can stretch progressive lays, which we'll get into probably mostly in our wildland section. Where we'll have like an 1.5 inch trunk lay, and then we'll branch off of that trunk with 1 inch, attack lines. Out in with Crook with our national deployments, we use a lot of 3/4 inch hose, which is actual garden hose fittings on it, but it's the same material as our wildland hose. It's just a 3/4 inch diameter. We'll use it for mop-up operations because it is very lightweight. You cannot pump wildland hose at 200 psi. You will blow it apart, so it has reduced pressure. Booster lines, these are the rubberized hose that's on the reel on the back of 926, on the back of 924, and on the top of 925. These are non-collapsible. The reason that they're non-collapsible is so that whenever they're rolled up like that, they can still flow water. So you can pull off 10 feet and still get good flow through that, or you can pull off all 200 feet. Um, I don't think ours are 200 feet. I think ours are probably closer to 100 feet. Um, but the concept doesn't really change. Ours are 1 inch diameter, and they're never to be used for building or vehicle fires. They were, and not long ago either. People would use booster lines for literally everything, for reasons unknown. Typically used for nuisance fires and flows less than 600 GPM. We'll use these a lot of times on wildland fires. They're very durable. You can drag it around behind the truck as you're driving the truck along. Um, they're heavy for sure. Is probably their biggest detriment, but they are useful for sure. We use the heck out of them. Hose construction considerations. Technology has dramatically increased the performance of fire hose, um, mainly in the form of friction loss. It resists damage from sharp edges, rough surfaces, sunlight, heat, mildew and mold, and long-term storage. There's been a lot of research and development that has gone into particularly the attack hoses, the 1 3/4 and the 2.5s that we use, and with good reason. It's a very important part of our kit. Hose demands and maintains ability to flow water and resist kinking, folds easily, and lies flat in a space efficient manner. This is a pretty well-known dichotomy. It's difficult to get good performance with both of these things. You can usually either get it to resist kinking, or you can get it to easily fold and lie flat. This new hose that we have, this key hose, it is some of the best technologically advanced hose when it comes to being flowed at a low pressure while still resisting kinking, but it is an absolute pain in the ass to get it loaded back on the truck. So you got to have the good with the bad. And that'll improve a little bit as it breaks in. But you see some of this older hose, and you guys have even seen as you've helped us wash and dry and maybe reload some of this hose. It's those older hoses, they fold in pretty nicely compared to that stiffer, newer hose. But that's the price we pay for getting tip-top performance. Hose construction. Typical fire hose has a liner with one or two reinforcing jackets. Um, the liner must be smooth and watertight, so it has a rubberized liner on the inside. And then there's going to be a protective sheath, and then there's the outer sheath um, that kind of protects it all. But um, the outer sheath is going to be the one that's taking the brunt of the sharp edges and everything, whereas the inner two sheaths are going to be taking most of the pressure. Um, but it does what it does. Hose jacket must resist the expansion of the waterway, so you don't want this to swell up. Kind of its job. Hose jacket types. Single jacket outer sheath protects the hose from damage and resists expansion. That's what we talked about, like our wildland hose. There's only one section, there's only one jacket in there. Whereas our structure hose is double jacket, provides extra protection, and most common. Um, yep. Hard suction hose. We beat this to death by now. That's our ribbed, you know, hard suction. Maintains its shape under vacuum for obvious reasons. Designed for drafting operations. And wire or plastic reinforcement maintains the shape because you can't have that collapsing while you're trying to pull a draft. Extruded hose, jacketless hose, both supply and attack hose, primarily used as supply hose, lightweight, tendency to kink, ultra large diameter hose available, 6 to 12 inch diameter. So there is no outer sheath on our yellow LDH right here. Fire hose flows are based on math and physics, like everything else in the world. Hose size and typical flows. So let's see, we have inch and 3/4. Typical flows between 95 to 200 GPM. Typically the smooth bore nozzles that we use with a 7/8 tip, we're flowing those at approximately 150 GPM. And we're using that as an attack line. Weight per 100 foot empty. So a 100 foot of hose is going to weigh 32 pounds. Weight per 100 foot full is going to weigh 152 pounds. Typical length is 50 feet sections. So if we have two sections of hose, they're going to weigh 32 pounds, or about 16 pounds each. And then you're going to have to drag 152 pounds. That's why you guys have all been through our physical agility test. You're dragging two charged sections of inch and 3/4 hose. So you're dragging, not quite 152 pounds because you're not dragging the whole length of it, but you get the idea. And then the 2.5 would be the next common step that we use. We can flow that between 200 and 325 GPM, which again is our flow. We also use that as an attack line or a hand line. 52 feet, so it's pretty comparable when it's empty, but when it's full, it's significantly increased in the amount of weight that you have to drag. That's why it takes some pre-planning and it takes some work to drag around a 2.5 inch hose by yourself, and it's typically in 50-foot lengths as well. On our tower, we talked about how we carry 3-inch supply line. So there's the stats on that. And then our 5-inch is the largest commonly found LDH slash supply hose. And that is, our stats right there. Our LDH is in 100-foot sections, and they're heavy. That don't sound right. Maybe they're 50-foot sections. They might be 50 foot because I don't think they're 110 pounds. They might be. All right. So hose couplings, key component in fire hose. Of course they are. Join and break apart hoses rapidly. We have threaded couplings or we have Storz couplings. Um, handle pressure and stress well. Yeah, they have to do that. Older couplings were made of brass. The ones that we have are made of hardened aluminum. So rocker lugs on both male and female couplings. That way we can use our spanner wrenches. Male couplings have lugs that extend the full length of the coupling. Female couplings have lugs only on the swivel. It's this section here. So if you're looking at this hose, this is the male end, this is the female end. That'll be important to know if you're ever in an environment inside of a house where you can't see, there's zero visibility, and you're trying to follow this hose line, and maybe you're trying to figure out if you're going back out towards the door or if you're going towards the nozzle. You can think about these couplings whenever you come across them. If you find a smooth section and then a small bump and then a larger bump and then you're back on hose, you know that you're going back out towards the fire truck, right? Does that make sense? Because our female end is always going to start at the fire truck. So the female ends are always going to be progressively pointing towards the door. Yep, this one's the opposite direction. And then this one, we don't have any LDH that is still threaded, except for our hard section. Spanner wrenches are used to tighten couplings. There's a million different designs of spanner wrenches. We have spanner wrenches inside of the engineer's compartment. You'll see those. We have spanner wrenches that you guys carry in the form of those snagger hooks, those red S hooks that we gave you guys. There's spanner wrenches. Some of you might have the yellow and black plastic foldable spanner wrench. Um, you also might have oh, this is the new one I just bought. I'm pretty excited about it. Oh, this is spanner wrench and cutters all in one. So I've got my spanner wrench right here. Um, and then pry bar. But those are some sweet cutters. So you can get all kinds of stuff with spanner wrench attachments on it for sure. Gaskets are installed on the female swivel. You always want to make sure that you have a gasket in there. Attached to hose using brass expansion rings. For the most part, we'll never take these apart, but it's interesting to know. Coupling expander used to attach the coupling to the hose. So repairing these things is it's definitely it definitely can be done, but nobody around here does it that I know of. Joining hose lengths is similar to tightening a nut and a bolt. Lefty loosey, righty tighty. Locating the Higby cut allows for faster coupling. Are they going to explain to us the Higby? Nope. So the Higby, all my fire hoses outside. Um, yeah, you can almost see it there, but the Higby is basically where the thread starts. It's that first thread up top here. That Higby, if you can kind of hook it into the female end, and then if you can get that Higby hooked, then you can rotate it from there. So it's usually a good idea. And if any of you ever remember, we used to do, probably not, we used to do races. That's what all them trophies are back there. Um, no, it's upstairs. Uh, but you would hold the male end in your hand with that Higby facing upwards, and then you would hold the female in the other hand, and you would hook that Higby in there, and then rotate. But, you know, we'll practice that. Storch couplings, you guys have seen these on our yellow LDH. They're sexless, so it doesn't matter. You can connect any of them to any end. You can flip them around and connect them. There's no male or female. They go both ways, as some would say. Right to Titan, they're still righty-tighty, lefty-loosey. That way dumb firefighters don't get confused. And then they have non-locking and locking styles. As far as I know, almost everything that we have, in fact, I think everything that we have is going to be the locking style. So you'll see we have these little levers that we'll play with when we go down there for training, but those are what actually locks those Storch connectors together. Storch connectors are bolted, Storch couplings are bolted to the hose. Retaining ring attaches the coupling to the hose. No male or female adapters are required, like we talked about. That's kind of the main thing with those, is you can lay them any direction. You can have a, you can have a truck lay from a hydrant, and then you could have another truck reverse lay back to a different hydrant if you had to. So that it opens up a lot of options for. We probably could talk about that real quick. So sometimes what we'll do, if we know, like if we get a structure fire, maybe we get a kitchen fire on a Sunday afternoon, and we know that we're going to get, 15 people down to the fire station. We might be in a situation where we might take the first due engine, maybe 921 is going to go out of the station, and they're going to go up there and say the fire is right here. They're going to pull up to the scene. That's got a hydrant right there. But anyway, they would pull up to the scene. They would not hit a hydrant, and they would make the initial attack. They'd go in and they'd start hitting that fire, and they'd get on the radio and they'd say, "Hey, 920, you need to bring us a hydrant with you." So they're going to make that attack because they know that 920 is right behind them. They were getting in the truck as they were leaving the station. So then 920 has the option of hitting the hydrant and bringing it to the truck, or coming the other direction and stopping at the truck and progressing to the hydrant, because these there's no male and female ends, so these LDH hoses can be laid both ways. But it's just kind of an interesting deal. We've done that before, but we still almost always start at the hydrant and lay to the scene. That way you don't have to try to turn around once you get there. Okay, so now we've got some silly videos talking about some different ways to
step on the hose just
put hose together
behind the male coupling. This action will make the threads tilt up. The firefighter can then, using both hands, hold the female coupling and mate the male and female couplings. The firefighter twists the coupling clockwise to join the hose together. This method can also be used to uncouple hose.
Nice work.
Step on the hose just behind.
Knee press.
Sometimes when trying to uncouple hose by yourself, you may run into a coupling that is too tight to use the standard foot tilt method. In this case, you can use the knee press maneuver. Bend the hose back and drive the male shank into the ground by pressing on the female shank with your knee. This compresses the hose gasket. While compressing the coupling with your knee, reach down and loosen the female swivel by turning to the left or counterclockwise.
Yep, so he's just taking the pressure off that gasket to be able to unscrew it.
Sometimes when
here's how we do the Storch coupling.
The Storch connection is a universal connection very common when using large diameter
It's probably
hose.
tiny for you
The
guys
ease
that are
of
on your
coupling
phone.
between Storch connections are inconsistent due to the condition of the Storch coupling, manufacturer, maintenance level, and whether they are locking or not. The firefighter grabs both couplings, aligns the tabs, and presses the couplings together. If you are using locking Storch connections, be sure to line up the locking tabs. Failure to do this will result in added difficulty during removal. The firefighter then twists the coupling clockwise until the couplings click into place, usually a quarter of a turn. If the couplings are non-locking, ensure that the lineup arrow indicator or cut coupling indicator line up to ensure that the couplings are fully coupled. To disconnect the Storch connection, depress the locking lever on each coupling. and twist the coupling counterclockwise to disengage the lock. One should always have a set of Storz spanners available in the event that the connection is too difficult to remove by hand. Each firefighter grabs a coupling, one male and one female. Now facing each other, the firefighter with the male coupling holds the male shank rigid at waist height. The firefighter with the female coupling then mates the two and turns the female coupling clockwise until tight. Both firefighters take a firm grasp of the couplings and then push toward each other, which compresses the hose gasket. They then use their body weight with their arm muscles contracted and stiffened and turn their couplings to the left or counterclockwise. Once the coupling is loose, the firefighter with the female coupling then turns the female swivel until the hose is uncoupled. Both firefighters Two firefighters each grab a coupling, lining up the tabs. They press the two couplings together. The firefighter then twists the couplings clockwise until the couplings click into place, usually a quarter of a turn. To disconnect the Storz connection, each firefighter grabs a coupling. In the event they are locking Storz connections, each firefighter depresses the lever on their respective couplings to disengage the lock. Each firefighter then twists the coupling counterclockwise until the couplings disengage. This is typically one quarter of a turn.
Okay. NFPA 1962 recommends inspection after each use for slippage on hose, which is like the coupling slipping past off the hose, or it could also mean like the threads slipping on them. Missing lugs that have been be ground off and maybe got drug, damaged threads, corrosion, loose collars, and make sure that it's got a gasket. Uh, hmm. Victaulic mechanical couplings can be used up to hose. It can be used on hose up to 18 inches in diameter. Interesting. Metal bands tighten in the grooves, making a watertight connection. I can't offer much about this one, guys. Okay. Well, besides that last one, does anybody have any questions on hose? Hey, Ray's here. Ray, did you get it hooked up okay? Okay. Okay. You can see the presentation and everything? Nice, nice. Okay. All right. We'll move on to um, hose appliances, fittings, and some tools. So the purpose of the fittings and appliances are to join two different hose sizes or couplings and to divide one hose into two. Combine multiple hoses into one. So, one of these that we've talked about so far was that Siamese LDH appliance that we talked about, bringing those two and a halves into that 5 inch. And there's others that we'll talk about in here as well. So describing hose fittings, begin with the female side. If Storz, begin with that. Identify the size of both ends. Identify threads, swivels, or lugs. Okay. So reducers reduce couplings from larger to smaller. So you might have like here's an inch and a half to inch wildland reducer. This one might be going from 2.5 to inch and 3/4, and this one might be going from a 5 inch down to a 2.5. So we want to have a lot of flexibility whenever we're working on different situations. So reducers are definitely something that we'll use in different situations, and they may be incorporated into Ys, like we'll talk about. Increasers does the opposite. Increases couplings from smaller to larger. Tristan, why do you think that they would be different? What's the difference between a reducer and an increaser? Yeah, exactly. Yeah, exactly. Yep. Um, the big thing between increasers and reducers is going to be that reducers are going to have a female threads for the larger side, and then male threads for the smaller side. Whereas increasers are going to have male threads on the on the larger side, and then female threads on the smaller side. Um, we don't use increasers very often. I don't know that we carry them on anything, but it's good to know about. Double fittings. So like this is to to join two male ends together to using a double female. We do carry a lot of double females, and we'll use those in quite a few different situations. And then double male fittings join two female ends together. We'll use these a lot as well. We use double males and double females quite often in wildland for different reasons. A lot of times, you may be hooking up to somebody's hose line, and it just happens to be, depending on the way you're working around those houses, it might have been laid backwards, and so we'll throw in some double females and double males, and we'll make it work. But we carry them on our engineers compartment and our structure engines as well. Adapters. So like one of the main adapters that we use is Storts to threaded fittings. So we can thread one of these onto our hydrant, and then we are able to come off that hydrant onto a Storts fitting, or we can thread one of these onto the side of 921, and then we can have Storts on there as well. So you can also use these to change the type of thread that you're using. Sometimes that'll be something that we'll do in wildland as well, or maybe we'll change to like a banjo type fitting as well. But there's a lot of different reasons that you would use these, but the concept never really changes. Pipe thread is a pretty common one that you'll find on some farmers' equipment. Elbows, exactly what they sound like. So like we have elbows on a lot of our engines on the intake to be able to get that intake to point down, because you don't want that intake to come straight at the truck. You want it to point down at an angle towards the ground, because whether you're using a hard suction hose or you're using an LDH, you don't want a hard kink or a lot of downward pressure on that. So we'll have most of our elbows are pretty much always pre-connected on those. So, and then caps and plugs are exactly what they sound like. They're used to cover or fill outlets and inlets. Keep the side of the truck looking clean and not getting a bunch of gunk in there. So, if you ever find that one of our caps is missing, that's definitely something we want to prioritize getting replaced, because we don't want a bunch of stuff getting into our plumbing in there. Um, So appliances allow water flow to be manipulated in different ways. That's the general purpose for all of these things. These appliances, you can, um, like we talked about with our Siamese Y. Well, some of these will do the same thing. We have a lot of Y appliances for um, different situations. We use these for reducers as well. If we're going to put our 2.5 onto the hydrant for like you guys' physical agility test, we put one of these onto our hydrant to reduce it down to 1 3/4, and then we could charge and uncharge either of these lines as needed. Um, and then, so single female inlet and two male outlets is almost always how these are set up. and then gated or non-gated, and maybe reducing. So like this would be reducing, since it's reducing from 2.5 to 1 3/4. This one looks like it's not reducing because it looks like these are probably both 2.5 here. Um, okay. This would be the opposite direction. I don't have anything like this. So this would be two female inlets. No, I lied. So the Siamese are that we talked about hitting the hydrant with if it doesn't have a steamer connection. That would have two female inlets. Um, has two female inlets, and then the Storch, which we also talked about, does not have a male or a female designation. So that would be that style. Um, And then I don't know if there's no other pictures of this, but these things have an internal uh, flapper, for lack of a better word. If one of these, say you blow this hose, that flapper is going to close over this side of it, and to make that water pressure is still going to go towards the truck instead of just going out right here. Does that make sense? So there's an internal flapper in there that basically pivots at that little rivet right there, pivots right here, and it runs this direction right here. When both of these are charged and flowing water, it stays centered and it doesn't impede anything. If any of these were to get shut down, it would flap over and it would close that side or it would close this side so that it does not backfeed that pressure to go through that blown line or other scenario there. Okay. Mm-hmm. 2.5, yep. Right. So I mean that's the general idea is we pretty much only use these on the hydrants that don't have that steamer connection because that steamer connection would be the more efficient way. But when we don't have that steamer connection, uh, two 2.5s or sorry 2 3 inch, they're 2.5 inch couplings, but it's actually 3 inch hose on those little pony sections. So that's going to get us pretty close to the friction loss of a 5 inch. Yeah. LDH appliances, that's fancy. Relief valves are often built in. Water hammer is of great concern with LDH and large flows. So on the side of the tower, on the side of 930, the inlet where you would normally hook in your large diameter hose, it has a built-in relief valve that looks similar to this one. So if you're ever flowing, if you're ever bringing water into 930 off of a relatively high pressured hydrant and you're wondering why it's dumping out the bottom right here, it's because probably if it's constantly dumping, it's probably because your relief valve's set too low. But then it will also, you don't want it set too high because what that relief valve does is if you're flowing in there and into the tower and somebody slams that valve shut that's on the tower, it doesn't hammer the system. It can kind of bleed off some of that pressure through that relief valve there. So that'd be the kind of the concept that they're talking about. Hose tools aid firefighters in the use of hose. This is a hose clamp. I think we'll talk about those. This is a standard classic spanner wrench. This is a hose strap. We have not many of these left. We used to have some of these that we would keep for dragging some hose around. A lot of times we'd have something on the back of a 2.5, but we've kind of gone to mostly webbing wrapped around, like the 5 inch. We'll have some webbing wrapped around the 5 inch to be able to get a good grab on it when we pull it off the truck. Spanner wrenches used for loosening tight coupling connections. So it says this not by accident. These are used for loosening tight coupling connections. Typically, whenever we connect hoses, we want those hand tight by design. We want those intentionally to be hand tight. We don't want to crank down on those things to try to get them monkey tight, because it makes them very, very difficult to get back apart. They have thick gaskets in there for a reason, and that's because we don't want them to be too tight. So spanner wrenches are used to loosen it. Now, with that being said, there are times where whenever you're connecting it to a truck, you might want to just make it tight enough to where it doesn't leak. And sometimes you might have to give it a little quarter turn with the spanner wrench, but they're you don't want to go cranking down on the hose couplings. Type varies depending on hose size and coupling style. This is for some booster reel stuff. This is kind of goofy here. This is for Stort's hose right here, and you'll see a lot of different designs as well, like we talked about. Just different stuff, and then like your snagger hooks that you guys have. There's a million different designs out there. Hydrant spanners. This is our classic hydrant wrench or hydrant spanner used to open and close a hydrant. This is that goofy thing that I said I'd never seen. I guess this is the wrench that you would use to open that thing. Probably in areas where they have problems with people getting into them that aren't supposed to be getting into them. Locking cap hydrant spanners for tamper-proof hydrant caps. Yep. So we're going to talk about some hose clamps now, it looks like. Stops water from flowing down a fire hose. Who was it that found a hose clamp in their wildland pack last? It was Zach. Yeah. Zach, you found a hose clamp? Yeah, you found a hose clamp in your wildland pack, and we talked a little bit about what that might be used for, but they were a lot more prevalent in the fire service back before we had um, as advanced of hose as we have now. Typically in the structure world, the hose that we have now has a very, very, very small chance of ever blowing while you're on scene. Whereas back in the day when you had junk single jacket hose all the time, you would consistently be having problems like that. Now in wildland, we blow hoses all the time, mainly because of the elevation gain and loss. We're constantly having to pump the stuff as hard as we can just to be able to get it to come out the other end. So we'll, if you ever go out with me, we will blow some hoses. So this is a screw down clamp. We're just gonna watch the video. He's probably gonna
Open up the hose clamp and place the hose inside. Close the clamp.
We don't have any of these that I know of, right, Ray?
Twist the handle clockwise to press the clamp down on the hose until the water flow has been blocked.
Pretty neat though.
To remove the screw down hose clamp, simply twist the handle counterclockwise to restore water flow and remove the clamp from the hose.
Yep, we have one of these bad boys right here.
Open
This is sitting underneath the stairs at the fire station right now.
Press down on the lever, engaging the clamp until the clamp is fully closed. To remove the hose clamp, make sure to stand to the side of the clamp. Do not straddle it or put your head in the path of the clamp handle. It is under extreme pressure. While putting pressure on the handle, slowly release the pressure from the hose, then remove the clamp.
Okay. Wildland hose clamp. This is the one that Zach found in his
hose
pack.
clamp is a small clamp typically used on wildland hose. Open up the hose clamp, placing it around the hose. Clamp down on the hose until the clamp is closed and the clamp lock can be engaged. To remove the hose clamp, grasp the clamp firmly and disengage the clamp lock. Slowly release the pressure.
Yep.
A wildland.
Okay, so here he's going to do like you might do with your garden hose.
To perform the field hose
We'll
clamp
take that
maneuver,
nozzle
create a
off.
loop in the hose. Using your body weight, press down on the loop to flatten it, restricting the water flow.
Yep.
To perform
Hose jacket. Man, we used to have one of these. I doubt we still do, but you would attach it around a leaking hose. We used to carry one of these on the truck when I first got on. You'd attach it around a leaking hose, and it does not slow the leak, but it could stop them. It would get you through the rest of the fire. Um, kind of a cool design. We sure are spoiled with the technologically advanced hose that we have nowadays, to where we don't have to worry about things like this. But yeah, they would use things like that. So hose rope tools, secure hose to ladders, fire escapes, and window ledges. Here's just a webbing tied to a hose. This is probably the most common method that we use. And here's kind of a strap. Here's one of those straps. I mean, there's just different methods that you can use. Here's
a large
nice.
foot is a useful way
Sorry,
to
Zach,
secure
these
or
videos are
control
getting
hose line on the
smaller and
fire
smaller.
ground. Using a loop of webbing, simply wrap the hose line with the webbing. Pull one end of the webbing loop through the other. Grab the end and pull tight.
Yeah. So he tied that webbing around there and he threw it over his shoulder. I mean, that's definitely something that would be a good idea to do on a haystack fire or something once in a
A
while.
large
But
foot.
yep, all kinds of stuff you can do with webbing. Chafing blocks protects hose from rubbing on pavement. Interesting. We don't have anything like that. Hose bridges protects hose if it must be driven over. So, you know, sometimes if you have hose running across the street, maybe it's going to be a long duration deal, or for whatever reason the chief's got to come through and you want to throw down the red carpet, you can throw these hose blocks to where they can drive over the hose. Again, we don't have anything like this. Okay, any questions on any hose appliances or hose fittings or valves or anything that we talked about? All right, we'll move on to hose testing and maintenance. Now, with that being said, it is 9 o'clock now, so we've been at it for 2 hours. I was planning on only going for 2 hours, but we are on slide 122 of 184. We've got some stuff to talk about with different ways to load hose. Obviously, this inspection chapter that we're going to do, we've got some hose load stuff. We've got some different hose bundles. Yeah, there's a few. There's actually not many. So I would estimate probably 30 minutes. Would you guys want to do another 30 minutes tonight, or do you want to try to do it another night before our training next 2 weeks from now? Anybody vote? Zach says do it tonight. Get it out of the way. Okay. All right. Basic hose testing and maintenance. NFPA 1962 covers hose couplings and nozzles, inspection, care, maintenance, and service testing. Okay. So, cleaning fire hose, wash with clean water, rinse on scene with a charged line. We honestly do need to get a little bit better about rinsing them on scene. And usually we just have, if you have muddy hose on scene, there's no way to really rinse it on scene because you're just rinsing it into more mud. But when we get back to the station, we kind of want to try to rinse it off before we put all that mud into our hose washer. You guys saw how nasty that hose washer water got when we were washing that hose the other night. Brush with a stiff broom. Cotton jacket hose must be dried before reloading. So we dry all of our hose before reloading. We don't want that nasty moldy hose in there. Um, this is we do have a hose washer like this that attaches to a fire hydrant. We use it once in a while. It's kind of neat. It's uses cold water and it uses pressure and it does a decent job. So loading hose, reload hose in a manner that puts the folds in different locations from the previous load. Okay, so what they're talking about there is they don't want a wear spot in the hose to where the hose is always being folded at the same spot for 5 years. You might develop a bad frayed area on that fold. Hose inspection. Check the jacket and couplings for obvious damage. Look for leaks while the hose is still charged, and repack only dry hose when in freezing climates. Um, yep. And so we want to do this on our own. We do now. Well, for the past few years, we've been hiring out all of our hose testing, and they will do these inspections annually as well. But we want to have an idea to where we don't throw a hose back in our crosslay that's got an obvious damage to that outer jacket, or will be that idiot trying to put a hose clamp on it or something. So hose folds. Creases develop if folds are left in the hose for long periods. Like we said, we want to kind of, pull that hose once in a while, which is good training anyway. Remove hose at least 4 times per year and rotate the folds. Yep, makes sense. Hose pressures. Service test pressure. Annually tested pressure, and it's stenciled on the hose. So the hose is going to be stenciled. This one says service test of 400 psi per NFPA 1962. Acceptance test, tested at the manufacturer twice the service tested pressure. So when they initially manufacture it, they might test it at 800. Whenever we bring the contractors out to test our hose, they test it at the NFPA recommendation per that hose, which on this hose would be 400. Burst pressure is tested by the manufacturer, and it is to be at least 3 times the service test pressure. Operating pressure, never exceed 90% of service test pressure, rarely greater than 250 psi. So if and I don't have stats on what our hose is, but if we use that 400 psi as a generalization to maybe be what ours is, even if you're pumping that at 250 psi, you're probably only doing that because you're going a long ways up in the air or a long ways away from the truck. I mean, it's very rare that we're going to be pumping anything that high, unless we're doing some kind of relay pumping operation and where we have something that's way out of control. But just pay attention. I mean, you'll notice if something's not sounding right. Hose documentation records must be kept of all fire hose. This is part of the service, as far as I know. That is, I guess maybe Ray does it, but a lot of it is attached to the company that we contract to test our hose for us. The size, length, and type. Each hose has an ID number and a date. You'll see those little barcodes that they put on there. Any repairs that have been made to that hose. And then the test dates and pressures that it was tested to on this hose testing log. So hose testing, visual inspection must be done before pressure testing. That way you're not, blowing out a hose that was obviously damaged and there's no reason to pressure test it. Service life is based on passing the pressure test, not age. So that's a good thing to think about. The service life is not based on age like your bunker gear is. It's based on if it passed or if it fails the test.
The first thing that needs to be accomplished is a visual inspection of the hose. Look for damage to the couplings, liners, and jackets. If the hose fails the visual inspection, the hose should be condemned. Identify the service test pressure. It is possible to test up to a maximum of 300 feet of hose coupled together as long as it has the same service test pressure. Find a safe location to test the fire hose and make sure to wear a helmet and gloves when performing the test. You can use either a fire department pumper or a hose testing machine to provide water and pressure for the test. Make sure the hose testing machine or fire department pumper is in proper working order. When using a fire department pumper for the hose testing, a gate valve should be used with a 1/4 inch drilled into it. During the high pressure portion of the test, the gate valve is closed, so if a length of hose fails, it will also not produce an extremely wild line. Begin by laying out the hose to be tested. Mark the coupling connections all the way around. These markings are used after the test to determine if the hose is slipped out or moved at its connection to the coupling. The perpendicular line that crosses onto the coupling is there to make sure the hose did not twist in the coupling during testing. Once the test markings at all couplings have been made, cap the last male in the test layout with either a special bleeder cap or a nozzle. Make sure both the nozzle end and the supply end of the test hose have been secured to reduce the chance of a wild line in the case of a rapid hose failure. The female coupling at the pump panel or the hose testing machine can be secured to the eyelet of the pump or hose tester using rope. In addition, the nozzle or bleeder cap at the end of the hose line is also secured with rope. Once the hose has been secured, charge the hose to 50 psi and bleed the air out of the line. Once all of the air is bled out, close the nozzle or bleeder cap and check the hose. This is done while maintaining 50 psi. Any simple leaks at couplings at this time can be addressed by tightening them with spanner wrenches. If leaks are discovered in the hose or at the shanks of a coupling at the hose connection, the hose has failed. Do not continue with the test. Remove the failed section or sections of hose and record the problems for repair. If it is not repairable, condemn the hose and cut off both couplings. Hose that has passed the initial 50 psi test and check is now brought to the full service pressure in a controlled manner. Once test pressure has been reached, allow 1 minute per 100 feet of hose to a maximum of 3 minutes for the pressure to stabilize. This stabilization period is not needed if using a fire pump. Once the pressure is stabilized, the service test pressure shall be held for an additional 3 minutes. During this time, visually inspect the hose carefully with caution, staying at least 15 feet away from the hose on the left side. The left side of the hose is determined by facing away from the pumping source. Never stand in front of the free end of the hose on the right side or closer than 15 feet. The reason the left side is safer is because the fire hose is constructed in such a manner that typically during catastrophic failure, it is more likely to rapidly move to the right. During the service test, if a length of hose bursts, the test must be terminated. The burst length of hose must be removed from the test layout and properly handled, documented, and tagged. Then the test should be repeated without the damaged section. After a successful test, the pressure should be brought down to equalize with the source. Then the tested hose should be drained and coupling markings examined for signs of hose slippage. If no slippage has occurred and no leaks were observed, then the hose has passed its annual service test. It should be properly documented and then placed into service.
Okay, so yeah, so if you see this machine right here laying around the fire station, this is what we used to use when we would test our own hose. Now the company that tests our hose for us, they've got a whole setup that they use. Um, but yeah, we used to do that part on our own. It would be a kind of a weekend deal that we'd all get together and do. Hose storage. Only in-service hose should be placed in storage. Out-of-service hose should be clearly marked. So if you have a hose that's out of service, tag it. We have some tags down there. Pink flagging is kind of a national standard for out-of-service hose. Although I don't have to see if we have any pink flagging down there, but yeah, tag it in some manner that nobody else tries to use for something else. I don't know if they'll talk about it. Yeah, they may or may not, but the other thing that we'll typically do is if you have if you're on scene and you have a junk hose, we'll roll it backwards. We always roll our good hoses anytime to where we finish with the female coupling on the outside. If you have a junk hose, you'll roll it backwards to where the male coupling is on the outside. That's also kind of a
Start at
standard
one
for
coupling and roll the hose along the ground
junk
until you
hose.
get to the other coupling. If you are rolling a hose that is to remain in service, start at the male coupling. If you are rolling a hose to be placed out of service, start at the female coupling.
There you go.
Start.
Out of service hose. Repairable hose should be rolled with the male end exposed. Yep, there we go. All repaired hose must be tested after repair. Unrepairable hose should have the couplings removed. So cut them off if the hose is going to be junked. That way nobody accidentally uses it. Fire hose should not be left hanging in towers for long periods of time. When drying is complete, take it down and store it properly. Some areas will hang their hose to dry. They don't have a fancy hose dryer like we do. Okay, yep, we're getting closer. We're gonna make it, guys. We're gonna make it. Introduction to hose storage. Commonly, does anybody have any questions about hose so far? Good. Commonly stored in hose beds, crosslays, reels, and compartments as far as being stored on apparatus. Stored based on tactics and the company's district. Hose may be pre-connected. Generally, attack lines are 1.5 inch, 1.75 inch, 2 inch, or 2.5. The attack lines that we use are all 1 3/4 inch or 2.5 inch. You guys, I think, know the difference by now. Usually 300 feet or less, may be mounted in a crosslay or rear hose bed. Female coupling is connected to a discharge, and male coupling has a nozzle. So they're talking about pre-connected hoses. All of our crosslays are pre-connected to the fire truck. The 920 and 921 both have a pre-connected flat load in the back of the truck as well, with a 2.5, and then there's also a second load in there that is not pre-connected. So it's important to know the difference between those, and we'll talk about those when we get down there for training. Flat loads are the simplest way to load hose. Reliable, easily deployable, predictable, and easily duplicated. So we use flat loads for our LDH. We use flat loads for all of our rear loads, and then we'll use. I'm sure we'll get to the cross lay, but we use we use a triple lay for our cross lay. So they're going to talk about some pre-connected flat loads.
Connect the female end of hose load to the male end of the discharge outlet. Load the bay using the flat load method. When you reach the 1/3 length of the hose load, extend that loop an extra 6 inches, creating a dog ear. At the 2/3 point, create a second dog ear, larger in length. Continue loading the remaining hose. Approach the bay, placing the larger dog ear around your shoulder and holding the small dog ear in one hand and the nozzle in the other hand. Walk away from the engine toward your destination. Drop the loop from your hand when it becomes taut. Drop the loop from your shoulder when it becomes taut. Now take the nozzle and move to your destination. Connect the feet.
Okay. Minuteman loads. So these are a very common type of load in a lot of structure departments, or in a lot of departments even. Usually uses no more than 200 feet of 1 3/4 hose. All of the hose is carried on the shoulder. Too much hose can cause tangles, and best suited for rear hose beds. What most departments use now will be a modified Minuteman, where you will only carry half of the hose on your shoulder, not all of it. But the
To
concept
load a
is similar.
150-foot, 1.5-inch attack Minuteman load, simply start by connecting the first 50-foot length to a proper discharge, and then make one pass on the bottom of the bed, placing the remainder of the length aside for later loading. Now join the remaining 2 links together, forming a 100-foot length. Place a nozzle on the male end and place the nozzle in the pre-connected bed on the side of the direction of pull. Once the nozzle is placed, simply flat load the rest of the 100-foot length on top of the nozzle. Once all of the 100-foot length of hose is loaded, couple the female coupling to the male coupling from the first length. As soon as this is accomplished, flat load the rest of the original 50-foot length of 1.5-inch attack hose on top of the 100 feet of 1.5-inch attack hose with the nozzle attached. You should end up with a tight finished Minuteman load. To deploy the Minuteman load, simply grab the entire bundle, placing the bottom of the load and nozzle on your shoulder. Make your way to your objective as the hose pays out with your forward progress. Once you reach your objective, flake out the rest of your working line and call for water. The pre-connected bed was completely cleared at the moment of deployment because all of the hose was placed on your shoulder. To load a 150-foot
triple load. This is the one that we use on our crosslays, designed to be easily removed by one firefighter, used for 150 feet and 200 feet hose stretches. Ours are 200 foot.
Create 3 equal layers of hose folded flat on itself like an inverted Z. As soon as the triple fold has been created, grab the layers together and flat load them. It is important that the last layer and nozzle remain attached to one another. Some departments use a strap to accomplish this. Others feed the loop of the last layer through the bail of the nozzle. Hold the nozzle in one hand and the layer it is attached to in the other and walk away from the pre-connected bed in a straight line. It is preferable to fully clear the bed before making a change in direction. Once the entire bed is cleared, drop the loop in one of your hands. At this time, you can take the nozzle and move to your destination. Hold the nozzle.
Okay. Dead load's not attached to any pump discharges when loaded. Our LDH is not pre-connected to anything. And then we have another load in the back of each truck that's also not pre-connected. Gives firefighters a working length of hose. Oh, sorry, this is hose finish loads. So we do have some finish loads down there. We will talk about it when we get down there. Many options exist to aid in hose deployment. Our finish loads are pre-bundled into these little bundles with those green hose straps. We'll look at when we get down there. Specialized hose packs or rolls kept on the apparatus. These are not connected hose bundles like we talked about with those backpack operations. This is a horseshoe bundle. This is similar to what we have as our finish load.
The horseshoe hose bundle, sometimes called the Denver hose pack, is easy to pack and can be used. Make the first bend. Fold the hose back just short of the male coupling, as tight as possible.
We'll go through that when we're down there because we're gonna.
The horseshoe hose bundle.
This is the donut roll. Protects the male coupling. We're not
The simple
use
donut roll
this
is made by folding a length of hose over itself in
really
half,
in our
and then
area.
pulling the male coupling back about 3 feet. You then simply roll down the hose toward the male and female couplings. The male coupling's threads end up on the inside of the female coupling, where the coupling is protected.
Kind of a neat deal.
This donut roll is easily secured by a large cut piece of truck tire, inner tube, or elastic band. The donut roll is also commonly put in bags called hose packs. Throwing the roll is the method whereby you grip the male and female couplings and roll the hose out in a bowling type fashion. This technique is used in open areas.
Okay, so supply line is usually deployed from the hose bed while the apparatus is driven. So like we talked about, we're going to stop at the hydrant, we're going to wrap the hose around the hydrant, and then the truck's going to drive off. Okay. Supply hose can be loaded with either coupling out, forward lay, reverse lay, or for any direction. We'll talk a little bit more about why, but our LEH obviously doesn't matter. And then if you have the, you know, female end on top, then you're going to be ideally laying from the hydrant back. Whereas if the male end is on top, ideally you're going to be taking the male end to the door. Jumper hose, this is what we have like in the back of the tenders, short lengths for making rapid connections, maybe pre-connected to the intake to speed connection. This guy keeps a jumper hose up there in their front bumper, where we keep a jumper hose for fighting fire with. Loading supply hose. Let's see, actually, I think that this might be pretty good to tie this in with the next section. So we might, let's see here.
Start by placing the coupling at the front of the hose bed along either the left or right edge. Lay the hose out flat toward the rear of the bed. At the rear of the bed, fold the hose over on itself, laying it flat up against the front of the hose bed. When folding the hose over for the second pass, offset the rear fold to lay the hose right next to the previous fold. Continue this pattern moving back and forth along the hose bed until the hose is completely loaded.
Okay, you guys are doing some mighty fine work there.
It is always best to load hose so the couplings are pulled directly off the hose bed and are not forced to flip over when deployed.
This is important though.
To avoid this, fold over an extra length of hose, thus shortening the hose and repositioning the coupling to allow it to deploy correctly from the hose bed. This is called a Dutchman.
You don't want those couplings to flip as they're being deployed. Okay. Typically, 3-inch hose is the smallest supply hose that is used. That's what we use on our tower. Higher flows are possible if dual medium hose lines are used. So that's why we use 2 3-inch on our tower. This is about medium diameter hose. So strong water supplies are needed if we're going to effectively supply medium diameter hose. Pumpers placed at the hydrant can increase, so I'm talking about relay pumping, can increase MDH effectiveness if you're going to need to use it. Supply hose lays. Choice of hose lay depends on tactics: forward lay, reverse lay, split lay. Supply hose lays are going to always be, the same for us with our our storage connectors. Forward lays, engine wraps the hydrant and lays a supply line towards the structure. This is how we typically do it. Depending on the length of the lay, an engine may need to pump the hydrant. I don't know that we're going to watch a 5-minute video about this, but let's watch him start it. He's going to get his hydrant bag, his gate valve, he's going to wrap it around. He's going to stand on it, then he's going to lay out. That's going to stop. He's going to flush it, he's going to hook it up. We'll do all that. We'll do all that in real life. Reverse lays, engine leaves, drops their line at the fire building, and lays to the hydrant. So the exact
Whether
same
supporting
thing.
supports at the fire building. Once on scene. Once the strip has been completed, the engine is then released to lay line to the hydrant. The company members left at the scene will then start to flake the pulled attack lines or supply lines and complete all the tasks necessary to be ready to call for water. The engineer, once released, will drive away from the fire, laying line to the nearest hydrant. Whether supporting supply or attack.
Yeah, not something we typically do, but you could see what the concept looks like. Utilized in both fire attack and water supply evolutions. Split lays, 2 engine work together to complete a supply lay. One engine's gonna not commonly used, however, it can be effective under certain circumstances. Okay. Drafting operations. Almost done here. We got a handful left. Drafting operations are common in rule settings. That's what we do. Dry hydrants can be connected to a lake, cistern, or swimming pool. Hard suction is often just placed into a body of water, which is how we typically do it. Floating strainers. Floats on the water surface, avoids underwater debris, can draft in shallow water. We don't have any floating strainers, but it's a cool concept. Round strainers, this is what we have, or barrel strainers, uses a rope to keep it off the bottom. Okay. Hydrant appliances. 2 types of hydrant valves. Water flow can be established through the initial supply line. Later arriving pumpers can add pressure without interrupting flow. That's pretty cool. I've never seen anything like that. 4-way hydrant valve. Huh. Hydrant gates. You guys have seen these. We use these during your physical agility test. Allow the use of other outlets without turning off the hydrant. So basically, it just gives you the option to turn off one of the outlets without turning the whole hydrant down. Carolyn automatic hydrant valves. I've never imagined. I can't even comment. Pressure reducing valves for high pressure hydrants. That makes sense. If you have a high pressure hydrant that's putting out more pressure than your pumper can handle, they might have a pressure reducing valve on there. We don't have anything like that here. Correctly using a hydrant is a critical skill. That is 100% true. Problems with hydrants should be pre-identified in your area. Okay. hydrant bags, needed equipment to make a hydrant. You're gonna have a pipe wrench, you're gonna have a cheater bar maybe, you're gonna have a maul or rubber mallet, hydrant wrench, locking spanner cap. We'll go through our hydrant bag and we'll talk about all the things that we have in ours. Hydrant bags allow the firefighters to have all of the tools needed to catch the hydrant, if you will. Wrap sufficient hose around the hydrant, flush it, and then connect your hoses. Like we've talked about a few times, and we'll get into all this whenever we are down
Approach the
there.
hydrant making sure to watch for traffic, and then quickly examine the hydrant for gross problems such as missing caps, broken or damaged spindles, or a damaged operating nut, as well as serious problems such as missing flange bolts or vehicle damage. If any are found, determine the hydrant operability. If operable, move on to step 2. Hydrant. When opening or this will take several turns.
Yeah, he's just flushing it. Okay, shutting down the water supply, so close the hydrant when directed, bleed the pressure, and drain the hoses. Replace the caps on the hydrant. And then when we do it, we'll talk about why you might want to leave those caps off for
After the hydrant is used, it must be shut down.
Okay, so that carried us through to the end here. Characteristics of water. We talked about that. We talked about some municipal water systems. We talked about rural and auxiliary water supply. We talked about hose construction and types. We talked about hose couplings. We talked about hose tools and appliances. We talked a bit about hose testing. We talked about different hose loads and rolls and lays. We talked about drafting operations a bit, and we talked about hydrant appliances. So when we go down there for our training night, we will get in depth about the hose loads that we use and how we, the reason that we use them. We're not this isn't part of the hose management section, so we're not going to be doing much deploying of those hoses. But we'll be looking at them. We'll wait till some of the firefighter operations to be able to, or firefighting operations to go through that tack line side. But we're going to spend quite a bit of time going through hydrants, going through our hydrant bags, looking at the tools in there, and hitting some of those hydrants. We probably won't be doing any drafting. We'll kind of see how things play out, but most of it's going to be kind of familiarization with the stuff that we talked about, correlating it to the equipment that we have at our station. So, any questions? I appreciate you guys sticking it out here. This is a half hour later than I wanted to go tonight, and this chapter is about 30% longer than most of the other chapters, if not 50% longer. So most of these training nights we're going to be like done by 8:30 or maybe 8:45 or so, but I appreciate you guys powering through this. Any questions? That's right. That's right. And that's we'll have the opportunity. It's unfortunate that it's going to be, a week and a half from now, but it'll be a good refresher by that point. Um, and I would encourage you. There's a lot of good information in that book. Like if you guys are into reading books and you have some spare time, I mean, read that chapter. Read the chapter. There's a lot of information that the person who wrote that chapter knows far more about this stuff than I ever will. And so it's probably worth the read for sure. This is pretty important part here. Um, but yeah, yeah. Anything, Zach? You betcha. Cool. Yeah, yeah, yeah. Well, that's good. Yeah, we have to get through this, but yeah. Cool. All right, guys. Well, it's about my bedtime, so I'm out of here. Thanks for coming in, guys.